Hello everybody and welcome to the latest edition of the Physics Corner. This is a series of videos in which we show how to set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're looking at something called a crumple zone. What is a crumple zone? Modern cars are incredibly safe compared especially to cars even a few decades ago, in that they're constructed in such a way that while if you're in a collision the car might be damaged severely, you, the passenger and the driver, are not. And this is how it works. The idea of a crumple zone is that if this particular section of a car is hit, it will literally crumple or fold in. Something like a spring of sorts, which is how we connect it to our physics discussions. Specifically, this is what's called overdamping, which is to say it will crush into a more compact shape, but then it will not rebound. It will not, of course, snap back to its original shape, much like a normal spring would. And that's interesting because that allows the crumple zone to absorb the energy of the impact as much as possible. So this is a safety measure. Whether you're hit in the side or in the front or the back of a car, you'll notice that a lot of these collisions will in fact damage the car. And of course it's a pain because it costs a lot of money to fix, but the people inside are safe, and that's far more important. So let's imagine we have the following situation. You're driving in a car. It has a mass of 1,200 kilograms at 10 meters per second, which again works out to be roughly about 22 or so miles per hour, and run into a brick wall, literal brick wall. The front of the car crumples, quote unquote, by a distance of 25 centimeters or 0.25 meters as the car is brought to a complete stop. What is the effective spring constant of our car? Okay, so let's see what we need to do. So our givens are mass is 1,200 kilograms, and the initial or original speed is 10 meters per second. Our final speed is 0, like that. And the distance that the car will crumple, so to speak, is 0.25 meters. The unknown is the spring constant. And while we're at it, we can go ahead and talk about the energy involved. I won't put that as an unknown, but that's going to come into play in this particular question. So, all right, so how would we go about solving such a question? Well, one of the things we know, of course, is linear kinetic energy. So kinetic energy of an object moving in a straight line is 1/2 mv squared in general. But in the case of a spring or spring-like material, and by the way, all solids have at least some ability to do this, the potential energy of a spring is 1/2 multiplied by the spring constant, which is the letter K, and by the distance the spring is either stretched or compressed. In this case, of course, we're compressing it, and that distance is squared, like that. So if it looks like these formulas have a similar sort of take on them, they do. A lot of energy formulas have this general appearance. This will maybe come in handy in some of your future physics questions, especially if you go further into studying other things, say electricity, magnetism, those kinds of ideas. That's partly because of the way that the math works and partly because of how nature works. But in any case, so this turns out to be relatively trivial as far as a math solution is concerned. I'll show you how. So the energy going into the collision, shall we say, is the energy coming out of the collision, if you will. The energy going in is all kinetic energy. And what happens if the car is brought to a full stop, there's no more kinetic energy. All that energy has been translated into the distortion or compression of the car. And we can talk about that or model that as spring potential energy, or if you prefer, elastic potential. All right, 1/2 mv squared for kinetic energy, and a 1/2 kx squared here for potential. Now, you could, if you wish, put subscripts on the v here, like we have up here. I'm going to skip that simply because there is no other velocity, right? Once the car comes to a stop, it's 0, and there's no real point in having it. But if you prefer to put that extra detail in, it helps you follow what's going along, be my guest. All right, so now it's just an algebra fight, and it's a fairly simple one, fortunately, at that. Notice 1/2 is common to both sides in this case. All right, we're solving for k, so divide both sides by x squared. Of course, looks like that. Now let's throw in some numbers. 1,200 kilograms for our car. By the way, that's the mass, more or less, of a medium-sized four-door vehicle. I sort of drew a van up there because, you know, I'm an old enough dad. I've got a minivan. I've got kids, but hey, whatever. Let's see. Speed is 10 meters per second. Whole quantity squared like that. And then x is 0.25 meters, and that also is squared like that. Okay. It's one of those things where you should also always double check my math, but if we do this, I'll round off appropriately. I get a number of about 1.9 times 10 to the 6th newtons per meter. Okay. And that is our spring constant for this particular car. Okay, now, is that a large or a small spring constant? This is actually pretty big. If you are used to playing with springs in, say, a lab class, probably the springs you're playing with have spring constants on the orders of, say, 10, maybe as high as 20 newtons per meter. They're usually not going to be much larger than that. So this is enormously much larger. But let's think about the situation. You don't want your car to flex under normal conditions. If you just touch the car, you don't want it bouncing back and forth, right? Which is what your lab springs are doing. You want to have a fairly stiff car, so to speak, that will take a lot to distort. But having said that, this is the result you get. All right, folks. A fairly short video today because the concept was relatively easy to handle. All right. The technical support for this program is from Sydney Gauchow and Sophia Turner. Our source of money comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla, thanking you everybody for your attention, and clear skies.